today's topic, flat earthers that believes that maps are compensated for magnetic declination. I'm in Poland working for the moment, therefore you will not see my lovely face. I don't have any studio here. Today's topic is Brian Leake, who thinks that maps are compensated for magnetic declination. And what does he use as a proof? A video from Mitchell from Australia. Let's start.
Alright, in this debate I'm going to point out how the sun angles in Sydney and Australia and other places don't work, and the globe model is not as perfect as people think it is, and this is the subterfuge, the magnetic declination.
What? Sun angles have nothing to do with magnetic declination.
So it says magnetic declination or variation is the angle on the horizontal plane between magnetic north, the direction the north end of the magnetized compass needle points, corresponding to the direction of the Earth's magnetic field lines, and true north, the direction along a meridian toward the geographic North Pole. This angle varies depending on position on the Earth's surface and changes over time. Of course it does.
And how does this work on your flat Earth? One magnetic north and one magnetic south.
So it has to be done on a horizontal plane, and or it doesn't work. I'm going to show you that later on in this presentation.
And of course he misunderstands horizontal plane.
But the first person to discover it, they say, was James Clark Ross back in 1831, where it was 70 degrees north and 96 west, which is insane. And then 70 years later almost, Amundsen in 1904 measured it at 70 north, 96 west. It barely moved a couple miles in 70 years, and then all of a sudden it just jumps up, but whatever. So they have the north geomagnetic pole and the south geomagnetic pole, and then they have the magnetic pole, north and south magnetic pole.
And he didn't react to the fact that you have a magnetic north and a magnetic south. 2 points on the Earth. How do you explain that on your flat Earth?
Currently we're at 86 north and 164 east, and so there's 3 poles. You have the geographic north, the magnetic north, and the geomagnetic north, and they all have their own purposes. So they don't even line up with each other. But so you wonder what's the geomagnetic poles for? And because they're at 80.8 north and 72.7 west. That's a long way off. That's in Ellesmere, Canada, and that's where people think the magnetic pole is, but it's not. That's what it says. What is the geomagnetic poles used for? It's the center of open magnetic field lines which connect to the interplanetary magnetic field and provide a direct route for the solar winds to reach the ionosphere. Yeah, it's the model they show you with the perfectly centered magnet in the center of Earth. It's just a bunch of BS. It's for make their planets work. It's not, has nothing to do with reality.
And there we did have a classic flat earther. Things you don't understand are BS.
So geomagnetic pole versus magnetic pole. The magnetic poles are the actual poles of the Earth's magnetic field, but are not antipodal, as they do not pass through the Earth's center. So for all the people who said just look at the South Pole and you could figure out the declination, that's wrong. They're not antipodal. It changes as it goes around on a globe. It's a jumbled up mess, but it's a fix-all, like I said, and it's going to become pretty apparent. So I was looking at the declination. I was like, how many poles are there? And so I looked it up, and it says 2 dominant magnetic poles and several weak quadrupoles, of which there are at least mathematically about 8 in number. There's all kinds of poles. They have to do this to make their model work. They have to turn and twist shit all over oblivion.
Once again, things you don't believe in or understand, call it lies and BS.
So here's where it shows that everybody refers to the northern hemisphere magnetic north. Okay, so do pilots fly magnetic or true north? Since the beginning of flight, pilots have been using the magnetic compass for navigation. It doesn't matter if you're flying a Piper Club or a Boeing 747. You'll find a compass in the cockpits of any aircraft. So this is real. How do we get to places? How do we fly? How do we know where we're facing?
This is the 6 basic instruments on an airplane. This is the heading indicator, a gyroscopic instrument. Basically it has a Euro compass, so north is true north. It's not affected by the magnetic fields. On an airplane you have magnetic compasses. As I show here, you have Euro compasses and you have GPS compasses. So you have 2 types of compasses that is not affected by the magnetic field. And in one of the main instruments on airplane, they choose to use a Euro compass, not a magnetic compass, in this heading indicator.
Or where we're heading, a compass. Or you could refer to a model, but you can't use that model to prove a model. That's what they do, and that's wrong. So look here, it says the following methods require that you have a general idea of your position. So if you don't know where you're at, you can't even use magnetic declination. So GPS receivers have internal data which aligns with the declination. So it's already in the GPS receiver. It's in the SunCalc data. So you can take your map and line it up with a known landmark to figure it out. But it says, look, it says here that the Polaris has almost a 1 degree radius around the North Celestial Pole.
This part is quite funny. He's on a page, Earth Science Australia, a e-learning page. And they are talking about Polaris and he don't react. Because do you see Polaris in Australia? Of course not.
So that allows up to 1.5 degrees of. So you go to look up what's the magnetic declination. So I looked at Perth, it says plus 14.62. And that didn't line up. So I check another place and it says 14.62, but then it says it's close to 0 on the same page. So then I check my location. It says negative 6 degrees in Jacksonville, Florida. I kept looking and it said 0 degrees or almost 0 degrees in another place.
And if I use the same webpage that he used when he looked at his hometown, if I use it on Perth, I did get this result. On that webpage, magnetic declination is calculated using the World Magnetic Model WMM 2020. And that's a rough model to calculate the magnetic declination around the world. But you can have big local variations depending on what the mountains or the rocks are made of, if it's iron ore in them and so on. Here we have an example. It's a small area around the town in Sweden, Sundsvall, and this is a measurement of the magnetic anomaly in this specific area. So the darker colors, the darker red colors, is a very strong anomaly. So you have a lot of effects that affect a magnetic compass. It also can be affected by the steel hull on a ship, magnetic equipment in motors and so on. So you have to adjust a magnetic compass also. These are used professionally.
Anyway, Mitchell from Australia goes to check the due east sunrise on equinox there right outside of Sydney, and SunCalc pegged it. It was perfect. But what they didn't tell you is that declination is included in all the calculations. They don't, but it certainly didn't line up with the compass. So let's take a look.
Magnetic declination was included in all calculations. What calculations? I choose to look at the Mitchells from Australia's video instead of using the parts that Brian used from his video. Let's listen to Mitchell.
Since the beginning of existence, I'm Mitchell from Australia, and today we're going to see the sunrise on the equinox. That's right, it's the 23rd of September here in Australia. That point right there, the edge of the rocks here, not the pointier rock, the one that's near the edge of the water there, that's where the sun's going to be coming up today. According to near maps, I'll show you. So, how long we got? About 4 minutes until the sun comes up. I'll just show you where I am. All right, it's a place called Kendall's Beach, and I'll show you this sign after. The sign says Kendall's Beach on that, just to prove exactly where I am. In near maps, we're going to see that bench. We're going to see that's the third. So 1, 2, third house. Yeah, in line with the third house. And on this side, got the shower. All right, simple stuff. So I'm looking out at those rocks over there, and now we'll look at near maps. We'll consult near maps to where I am looking to get a proper bearing. Okay, see what we can see on near maps, because what we see on near maps, yeah, it's the layout of the land, but what they don't tell you is that magnetic declination is already built into near maps.
What is he talking about? Maps are orientated against true north. So near maps or Google Maps, it don't matter. They are all orientated to true north. They have no compensation for magnetic declination. That's just stupid. If you look at charts used at ships for navigating longer distances, the declination is marked out. For instance, this is a chart from the area south of Sydney. This line indicates a declination of 14 degrees east, and it tells us that it's no annual change. And this line is 15 degrees. And if we move to the part showing New Zealand, this line goes through Wellington and it's 22 degrees east, and the change is 1 minute east every year. And this line south of Wellington is 23 degrees east, and every year it changes 2 minutes east.
In Google Maps. Alright, so Kendall's Beach. Hope everyone can see that. It says Kendall's Beach right there. Put it over to the camera. Alright, so zoom in here. I've got the park bench. Zoom right in, park bench, the shower, and I'm right there, in between. And like I said, 1, 2, 3 houses, right in line with it. Okay, so I'm going to put a little marker there where I am. We're going to look at these rocks here. And probably more in between. Yeah. So 91 degrees. 91 degrees to those rocks right there. Okay, that's what it says on near maps. That's what's going on at the moment. Sunrise time in Kiama. That's where I am, Kendall's Beach, Kiama. Right there says Kiama. Today on the 23rd, it should be 5:45 and it should be 91 degrees. All right, the sun is just about to come up straight ahead. And it is going to be, it's looking like it's going to line up pretty well with those rocks. That's exactly where the sun's going to come up, right there, as predicted by near maps, which is absolutely correct. But as I'm going to show you afterwards, using my compass, the only true direction that we can ever achieve magnetic north, from magnetic north, that sun right there, is not rising 90 degrees east. There it is, right there. And exactly where I thought it was going to be.
And this is exactly what we are supposed to see on our globe, rotating around a sun far away. And why wouldn't it correspond with what you predicted? You used a map based on a globe.
A fair bit above the horizon, we're going to measure with the compass the bearing. I wonder if we can do it here now, actually. All right, where's the... I'll line this up. All right, so if we're looking... Yeah, I don't think you guys are going to be able to see it. We've seen the sunrise. We've proven geographically that the sun will rise today on the equinox, what's called an equinox, right there. Okay, that's what we saw. Go back in the live stream. If you missed it, go back in the live stream and you will see that the sun rose from those rocks there, right there as predicted. Yep, we knew it was going to happen. And that's not because, definitely not because it's a globe. It's not a globe prediction, not a scientific prediction. It's just something, it's a cycle. We knew it was going to happen. All right, so it was going to rise right there. And that's what it did. Yep. Now that is according to the map, which has inbuilt magnetic declination. Magnetic declination is already built into the maps. Because when I use my compass, this thing right here, the physical compass that I'm using to measure something, this is the only way that we can get a direction, a true direction. The only absolute direction is magnetic north. And from magnetic north, where are those rocks? Those rocks are not 90 degrees. I think everyone can agree that the compass is not going to line up with geographical north, what's on the map. And if you do agree that it does line up, then I don't know what you've been looking at in your navigation. But this thing right here, the compass is the only thing that can get an absolute direction, the only thing that we should be using to get directions, because on maps like Google Maps, Near Maps, any maps that has a built-in magnetic declination, you are not going to line up what you see with the compass to what you see in reality. The sun, yes, rose here, but the compass did not measure 90 degrees right there. The compass measured 81 degrees. 90 degrees was over here. So I wouldn't even see the sunrise if it measured 91 degrees via this compass. Yeah? That's where 90 degrees is on my compass.
Oh dear, he don't understand what magnetic declination is and how you use it. Oh dear, you have to compensate for this in your magnetic compass. You don't compensate in the maps. So he didn't show his measurement with the compass, but let's calculate the declination on his location. We use Mitchell's 81 degrees and then the declination, let's use 13 degrees and we get 94 degrees. Quite close to the 91 degrees. So we have a small error somewhere here. It can be Mitchell's measurement on the map, or he used the compass a bit wrong, or something else. But basically I've proven that the magnetic declination is correct and that the map is not compensated for magnetic declination. And this rubbish about that it's only magnetic compasses that you can use. A better one to use is a gyro compass. It's not depending on compensating for declination. It always points at the true north, and the same goes for GPS compasses. Otherwise, you have to have knowledge in this how to compensate for the declination, something that Brian Leake don't have, and certainly not Mitchell from Australia. And then we continue with Brian Leake's video.
So speaking of other people, they said just check your sun at high noon. But if it's, here it is 5:45 in Sydney, and it's gonna, if it goes 15 degrees an hour, it's gonna line up 6 hours later north. So that's not gonna tell you where your true north is. Anybody who tells you that is not thinking. I mean, basically they're saying that if you have magnetic declination that's off, then your sunrise and sunset's gonna vary wildly.
Is he for real? Magnetic declination have nothing to do with the sun.
And you see here, it just goes on a 12-hour day. And so the time of day would have to vary too. Look, this is for Australia. See how all these continents shows them flaring out. And so here's another, they have to spread the map. They're spreading a flat map. So this is east.
So these declinations are used to spread out the flat earth map to fit to a globe model that you don't believe is real. Oh dear.
Or this is to the right of the Bering Strait. And it's all east declination. Then you cross the Bering Strait and you go down and it's to the left. So there's a zero line right there, and they just basically spread it out. That's all they're doing. And I mean, if you look at the magnetic declination maps, it's pretty obvious. They're just spreading everything out. So here's due east. This is due east with no magnetic declination. You see the angle when I zoom in. It's going to be 90 degrees to the meridians. And so this is about 12 degrees underneath. Does that look like a 11 degree angle? No, so you have to use a flat plane. That's more than 11 degrees. It's like 25 degrees. And that's basically from Sydney. Now here, so what I do here is I'm showing you 86 north, 164 east. That's the magnetic North Pole. So I'm going to trace it down to Sydney. It's a straight shot. Look, that's where the magnetic North Pole is. There should be no declination if that's what we're going off of, because look here, all the way down to Sydney, it's a straight line. So why would there be any declination? Watch as I back out. It follows right along the meridian. They must be talking about geographic or interplanetary North Pole. They just confuse us. Look, that might be off a degree, if that. It's insane.
When you're navigating, you aim for the North Pole. When you navigate, not the magnetic pole. As you mentioned in the beginning, the magnetic poles are moving. Oh dear.
So next I'm going to check the South Pole. And I'm wondering, why do the Southern Hemisphere continents not use the South Pole for declination? But look, so there's the South Pole over about 30 degrees off that way. So you're not going to use the South Pole to get your declination in the south, and you can't see Polaris. And the sunrise, I mean, look at 90. Here I draw 90, and the yellow line is the due east, and there's the 90 from the South Pole. So think about this: if you're going to make a map to start with, and you have nothing but a blank canvas and a compass, so what are you going to do? You're going to draw it out basically, or you're going to put together a bunch of local maps, and you're going to go by the compass reading. But if you already have a model, you're going to have to make adjustments to make it all fit into your model, and that's what they do with magnetic declination.
And that was the end of Brian Leake's video. Oh dear, what a mess, what a stupid video. And this is hilarious. One fool is using another fool to prove flat earth. Oh dear. Last last weekend I was in Ukraine and delivered some drones and met some of the soldiers that are using the drones we are sending to Ukraine. More about that in my latest live. If you want to help me help Ukraine, please use PayPal, link in the description. And that was all I had for you today. I'm not sure when I will be back with a new video. Thank you for watching. If you liked it, become a member, subscribe, hit like, or just come back next time I'm showing a video. Have a lovely day all. Bye.